part of the boot camp, which is sort of a mini course organized by Kunal, and he'll give the first part of it. And I just wanted to, there are a bunch of organizers listed for the workshop, but John Ullman, who was there, but there he is. John Ullman did a lot of the organizational work, so he should get it. And so we're really very lucky and happy to have Kunal.
Great. Thanks for inviting me. So I guess I will give some kind of a tutorial on large-scale differentially private machine learning. I will not assume anything other than what Kobe already said. So I'll start with the basics. We'll go over the definition, some simple mechanisms. So I guess for the first 2 hours, I'll talk about differentially private learning in the central model, where you have a trusted curator who collects the data set and does learning on top of that. In the third hour, Ilya will talk about learning in the local model, where we do not assume a trusted curator. And I believe the current plan, which isn't fully solidified yet, is to have Steve Chen, another colleague of mine, give a demo of the differentially private machine learning library that we've built at Google and open sourced. And if any of you want to try that library out, we'll have a demo of that to see how it actually works in practice. Okay, so I'll start with the basics of differential privacy. We'll then apply them to some machine learning tasks, including, I guess, in the second lecture, kind of training large machine learning models. And then just so not everyone, or just so some of the people are already familiar with this work, so just to give them something, I'll talk about some recent results which are applicable not just to differentially private machine learning, but I think are more interesting from just a differentially private algorithm or differentially private meta algorithms design at large. I'll try to go slowly. If there are any questions, do stop me, and hopefully everything should be relatively simple. Okay, so let's start again with the definition of differential privacy. We say a mechanism M, which will map a data set. So a data set is in D to the N. There are N people in the data set. Each of them contributes an element of D. The mechanism will output something from some abstract range space R. And R can change between different mechanisms, of course. We'll say this mechanism satisfies epsilon delta differential privacy if for any immeasurable subset of the range and any pair of neighboring data sets D and D prime. It is the case that the probability of this event S under D is within a e to the epsilon multiplicative factor of the probability of that event under D prime plus an additive delta. Right, so think of e to the epsilon. When epsilon is small, this is like 1 plus epsilon. So these two events are relatively close. Even if epsilon is a small constant, this is still giving you some guarantees on how large the ratio of these two events can be. We'll think of neighbors as two data sets that differ in the contribution of one person. For the most part, we will imagine each person contributing one row to the data set, but there's nothing in the definition that requires that to be the case. And in fact, some of the work I'll talk about will have the property that one person contributes some large chunk of data. We'll have to redefine the notion of neighborhood in that case and still get privacy. Okay, so I guess, so I'll deviate a little bit from the usual treatment of differential privacy for reasons that will become clear. So a central concept in this talk will be this notion of the privacy loss random variable. So what is a privacy loss? Privacy loss random variable is a lot of notation, so let's go over it slowly. So first, consider the following function, z, which takes an outcome. So O is an outcome in the range space of the algorithm. This is a possible answer given by the mechanism. And let me look at the probability that M outputs this value on D. Divide that by the probability of the same event, same outcome on D prime. And look at the log of this ratio. This is the real number. This is the ratio of probabilities, so it's obviously positive. So taking logs is valid. But this can be positive or negative. This ratio is roughly, if I was confused as an observer, if I was trying to determine whether the actual data set is D or D prime, this ratio is how much is my posterior different from my prior on these two events, given the outcome O. Right, so I come in with some beliefs. I think maybe it's equal odds that Kobe is TCS plus or not. Then I see the outcome of the mechanism, and based on the outcome, my odds between these two events change. This ratio is exactly capturing how much have those odds changed. Okay. This definition kind of makes sense when the output space, when the mechanism is, when R is discrete. When it's continuous, we look at the ratio of densities at some point O. Okay, so that defines a function z. Note that the z is the function of m, d, and d prime, though we will omit these when convenient. The z maps any output to a real number. The privacy loss random variable is defined as follows. I sample an outcome from M on D and then compute this scalar function z on that outcome. So I'm running the mechanism on D, looking at the outcome, and I'm asking what is the value of this privacy loss function on that outcome. This is a random variable because M is a random variable. And this is the random variable that will be to a large extent very important in this talk. Yeah.
So this function depends on D prime. I'm a little confused on what they are.
So D and D prime are two neighboring data sets. So I'm fixing two neighboring data sets,
Okay.
fixing the mechanism, and looking at this function, this random variable z. So to be precise, this z is a function of m, d, and d prime. There are three parameters associated with this definition. I'll omit them when convenient, but for the whole talk, we will fix d, d prime, and m. Yeah.
How should we interpret the range of the mechanism, say R, in the context of machine learning?
So it could, for example, be the model output by the mechanism or the parameters of the model. Right, so in the machine learning context, the mechanism will take a data set, the training data set, and output a machine learning model. It could be a deep model.
For example, the parameters will be
Yes. Yeah. R is the set of all possible parameters. O is one specific set. O is one specific setting of parameters. Any more questions? Yeah.
Sorry, you said that D and D prime are neighboring. What does that mean, neighboring?
So neighboring is what we talked about in the last slide. Neighboring data sets are two data sets that differ in the contribution of one person. In most cases, if every person contributes one row to the data set, D and D prime differ in one row. So in D prime Kobe's data has been released from the data set, D has Kobe's data. Okay, so with that in mind, let's go back to the definition of differential privacy. So even before this, pure differential privacy or epsilon zero differential privacy says that for every D and every D prime, that is a neighbor of D, the privacy loss random variable is always bounded by epsilon. So the privacy loss random variable was this log of this ratio. Pure differential privacy says that this is at most e to the epsilon times this. We hit it with a log, we get something that's always bounded by epsilon. So differential privacy fundamentally is talking about this random variable. Pure differential privacy says that this random variable is always bounded by epsilon. And epsilon delta differential privacy talks about the tails of this random variable. It says that the probability that this random variable is exceeds epsilon is at most delta. So this is not obvious, so let's give a proof. Okay, so good. So let's call B the set of all outcomes where this random variable is larger than epsilon. So now we'll write probability that MD is in S can be broken up into the contribution coming from B complement and the contribution coming from B. The second part we will just upper bound by the total probability mass of B, which by assumption is at most delta. When we are in B complement, the privacy loss random variable is bounded by epsilon, which means that the ratio of probability of MD being a certain outcome is at most e to the epsilon times the probability of MD prime being that same outcome. So if I kind of write this as an integral over the probability space, term by term the probability is changed by at most e to the epsilon, so I get this bound. Good. So what we have said so far is that differential privacy is talking about controlling the tails of this random variable. Okay, so keep that in mind. Now let's talk about about an actual differentially private mechanism. So here's the simplest or one of the simplest differentially private mechanisms, which is known as the Gaussian mechanism. This is a mechanism for releasing an approximation to a function q on the data set, which is just the sum of q applied to individual elements of the data set for some q between 0 and that maps every data set to be something real number between 0 and 1. Think of q as a predicate. It counts how many people satisfy a certain property. So q of a certain person is 1 if they satisfy the property, 0 if they don't. Q of D then computes the total number of people in the data set satisfying this property. The Gaussian mechanism says compute Q on the real data set and then add noise proportional from a Gaussian distribution with variance sigma squared. So this is what the distribution of this mechanism looks like. So here's the theorem we'll prove. If I set sigma appropriately to be something like square root log 1 over delta divided by epsilon, under some mild technical conditions, this mechanism is epsilon delta differentially private. Okay, let's prove this. So first let's go back to our privacy loss random variable. The privacy loss random variable at some point x is a real number now. Okay, so let's just shift things around. Let's, without loss of generality, assume that q of d is 0 and q of d prime is -1. This is just shifting This mechanism is kind of translation invariant. So this is not, this is without loss of generality. Okay, so what's the probability density at a point x when I sample from M of D? It's just e to the minus x squared over 2 sigma squared divided by some normalizing constant. When I change the mean of the Gaussian from 0 to minus 1, the density at x goes down to something like e to the minus x plus 1 squared over 2 sigma squared. Simple algebra, this is just x plus 1 squared minus x squared over 2 sigma squared, which is 2x plus 1 over 2 sigma squared. So we've computed the privacy loss function for this mechanism. Recall that we wanted to bound the tails of this privacy loss random variable. So we'll take a leaf out of kind of classical work on bounding tails of random variables. So if you ask a probabilist, how do you bound tails of random variable? The standard way is to use moments. So I have a positive random variable. The probability that it exceeds epsilon is the same as probability e to the alpha times that random variable exceeds e to the alpha times epsilon. I've just applied a monotone function here. And now I apply Markov's inequality. The probability that a positive random variable exceeds some quantity is at most its expectation divided by that quantity. And I've introduced this alpha. We'll fix that later as needed. This is true for any alpha. Okay, so now we know that if you want to bound this quantity, it's enough to bound this expectation. Okay, so let's compute this expectation. We are trying to bound e to the alpha times z of x, where x is, recall, drawn from n0 sigma squared. Z of x is just 2x plus 1 over 2 sigma squared. The 1 over 2 sigma squared is independent of x, so it just comes out. And we are left with computing this expectation when x is a Gaussian. This is an easy exercise. Let's do it. This expectation is an integral of this quantity, the quantity we are taking the expectation of, times the density at x. There's a normalizing constant. I've written it down, but you don't actually need to know what it is. Usually you don't remember. Okay, so let's expand this out. I have a minus x squared and a 2 alpha x. Let's try to complete the square. So this is x squared minus 2 alpha x. Complete the square to get x minus alpha squared over 2 sigma squared. And to do that, we had to add, we had to subtract alpha squared over 2 sigma squared, add that back. This is an equality. Why did we do this? This now is a constant independent of x. This part is the density of a Gaussian centered at alpha. Is the integral of the, so I'm integrating the density of a Gaussian centered at alpha. That adds up, that computes to 1. So I'm left with e to the alpha squared over 2 sigma squared.
We still have, I see. The constant
The
cancel.
normalizing constant is exactly what gives me 1. Right? So that's why I actually didn't even need to know it. Good. So let's plug that back in. And we get that this density is e to the alpha plus 1 over 2 sigma squared. Let's plug that back into the tail bound we were trying to compute. We have this e to the alpha plus 1 over 2 sigma squared as this expectation. Divide by e to the alpha epsilon. And you get this funny expression. To keep the math slightly simple, I'll assume alpha is at least 1. So alpha plus 1 is at most 2 alpha. So I get this bound. Okay, so I have a difference of two terms. One is alpha times epsilon. The other is alpha squared over sigma squared. I want to make this smaller than delta. Right? I want this e to this whole expression to be smaller than delta. And the simplest way to try to do that is to make the negative term 2 ln delta, 2 ln 1 over delta, and make the positive term 1 times ln 1 over delta. So let's do that. I'll set alpha to be 2 ln 1 over delta over epsilon, so that alpha epsilon is exactly 2 ln 1 over delta. And now I'll set sigma so that the first term becomes 1 times ln 1 over delta. And you get ln 1 over delta minus 2 ln 1 over delta, so you get delta here. And now I can read out what sigma ensured that. Sigma squared here turns out to be something like 4 ln 1 over delta over epsilon squared, which is basically what I claimed. So sigma is 2 times square root log 1 over delta over epsilon. This is not the tightest bound you can prove. There are better bounds available, but this will be convenient. And I guess, I guess I wanted to show this approach to proving things, which is why we proved a slightly weaker result than we can prove. But note that the only property of this Q function I used was that QD and QD prime differ by at most 1. So if you have some other function Q that maps data sets to real numbers, it satisfies this property that for any two neighboring data sets, the difference in Q is at most 1. The same proof goes through, unchanged. The largest difference between the value of Q on two neighboring data sets is what we call the global sensitivity of Q. Here I'm saying that if the global sensitivity of this function Q is at most 1, I can add Gaussian noise and get differential privacy. There's more. The same proof, essentially unchanged, goes through if I'm trying to compute a vector function rather than a scalar function. So imagine you have a function Q that takes the data sets and maps it to some k-dimensional vector. And it has the property that the 2 norm of the gap between QD and QD prime is at most 1. Then if I still add noise, which is proportional to sigma squared, I get epsilon delta differential privacy. The proof of this is essentially identical. I'm still measuring the density. I still want to talk about the ratio of density, about computing the ratio of densities at 2 points when I've moved the mean by a certain amount from Q of t to Q of d prime. And note that if I just draw the line joining them, if I rotate space so that the line joining QD and QD prime is my x-axis, Gaussians can be written as a product distribution over any rotation. In all the directions other than this one direction, the density function is exactly the same. In this one direction, I'm just using the one-dimensional argument. Questions? Good. Okay, so let's think about these moments for a little bit longer. What we showed was that for the Gaussian mechanism, the expectation of e to the alpha times this privacy loss random variable is something like e to the alpha squared over 2 sigma squared. Right? And if you think about this, this is a little strange at first. Why is it strange? So sigma was something like 1 over epsilon. Right? So this quantity is something like e to the alpha squared epsilon squared. Differential privacy says that the z is bounded by epsilon. So if that's all I knew about z, this quantity would be e to the alpha times epsilon. The scaling in epsilon would be linear in the exponent, and I'm getting a quadratic scaling in the exponent. Why is that happening? The reason that's happening is that the privacy loss random variable is a ratio of probabilities. If the ratio of probability is large at some x, it has to be small at some other x. So at a very, so if you think of, say, the Gaussian distribution, if x is sigma, this privacy loss random variable would be e to the alpha over sigma. But there's an equal chance that x is actually minus sigma. In which case, this privacy loss random variable is something like e to the minus alpha over sigma. And if you average these two out, so let's do the Taylor expansion of e to the alpha over sigma, e to the minus alpha over sigma. If you have matching positive and negative terms, the alpha over sigma term will cancel, and what you will be left with is the second order term. And this is not true. This is not just true for the Gaussian mechanism. This is a much more general statement. If you have any epsilon differentially private mechanism, then the expectation of e to the alpha times the privacy loss random variable grows as e to the alpha plus 1 times epsilon squared over 2. So even though this privacy random variable is only bounded by epsilon, the moments get to epsilon squared. Recall epsilon is usually less than 1, so epsilon squared is a lot smaller. Okay, so let's use this to prove a very important property of differential privacy, which is composition. So composition says that if I have a sequence of differentially private mechanism, M1 through Mk, and suppose each one of them satisfies a certain differential privacy guarantee, I'll call it epsilon 0 dp. I want to ask, what is the privacy of the full interaction? What can I say about this whole sequence of interactions? I'll call that M1 through K. So I'll call that M1 through K, and I want to ask what's the privacy loss random variable corresponding to this full sequence of questions. Okay, so let's write this down. Just by definition, this is log of this ratio of probabilities. Now note that the randomness used in the ith mechanism is independent of everything that happened in the past. So if I condition on the previous outcomes, mi of k has its own internal randomness, which is independent of all past events. So this probability can be replaced by a product of probabilities. Yeah.
Again, I'm not very sure about the independence between each mechanism. For example, let's say the mechanism is training a neural network, and each time we need to use the outcome of the previous mechanism.
So you're absolutely right. I'm kind of lying here. If I had to be precise, what I should really say is conditioned on m1 through I minus 1 being equal to O1 through I minus 1. And the property we are using here is that even conditioned on the previous outcomes, I may be running a different mechanism that depends on the previous outcomes, but this ratio for whatever mechanism I choose will be bounded because that mechanism conditioned on the past is still differentially private.
I guess you sort of, like that's an assumption maybe that maybe wasn't obvious. So like you're kind of saying every mechanism is epsilon differentially private no matter what the previous mechanisms did.
Yes.
Perhaps you can think of a choice function by an adversary or whatever, or the analyst that chooses mk based on the previous.
Yes.
Then fix any choice, and for any choice, the output mechanism is differentially private. So the choice of the analyst is always a differentially private mechanism, and hence this is
Yes. And I guess once we have these products, we kind of compute log and product to get sum of logs. And essentially what we are deriving is that the privacy loss random variable for the full sequence is the sum of the privacy loss random variables of individual mechanisms. And I guess here, as we said, this mi actually may depend on previous outcomes, but we'll assume that no matter, for every choice of mi, we have epsilon naught differential privacy. Right. So at this point, we can easily prove what's called the basic composition theorem in differential privacy, which says that if you have k epsilon 0 differentially private mechanisms, their composition is k times epsilon 0 differentially private. Why? Because epsilon 0 differential privacy says that this is bounded by epsilon. I'm adding k of these, so I get k times epsilon. And I guess this can be extended more generally to epsilon delta differentially private mechanisms with different values of epsilon I and delta I. And if you work a little harder, you can show that this adaptive composition satisfies summation alpha I and summation delta I differential privacy. But we want to prove something stronger. This is a useful result, but this is much weaker than what's true. So let's prove the stronger result. So let's go back to our moments method. We want to bound the probability that z m1 through k exceeds epsilon. So let's use again our favorite Markov's inequality on the exponential. So we just need to estimate the expectation of e to the alpha times z m1 through k. Right? But recall that z m1 through k is just the sum of z mi's, where again they are kind of conditionally independent based on the past. And because they are independent, I am looking at the expectation of now a product of random variables which are independent. And in this case, expectations and products commute, and I get the product of the expectations of individual e to the alpha times zi's. Each of these mechanisms satisfies epsilon 0 differential privacy. So this quantity is bounded by e to the alpha alpha plus 1 epsilon naught squared over 2, which is what we argued earlier. There's k of them, so I get a k here. And if you just kind of rewrite that, you get something like this. And this should look interesting because instead of epsilon naught times k, I have because I had a squared here, this looks like epsilon naught times square root k squared. And I guess once again I can do the same trick. I have this this function which is a difference of two values. Let me set this to be twice log 1 over delta and pick parameters so that this becomes log 1 over delta. You do that, and essentially that ends up to setting epsilon being epsilon naught times square root 4k ln 1 over delta. So if I set epsilon to be epsilon naught times square root 4k ln 1 over delta, and then choose the best alpha based on that, this probability can be shown to be bounded by delta, which means I've shown epsilon delta differential privacy for this value of epsilon. I'm making an assumption here, just similar to the previous case. I have alpha plus 1. So to keep things simpler, I'll assume alpha bigger than 1. But the whole math can be done without making that assumption. And what you would get is a slightly more nuanced statement, which says that the adaptive composition of k differentially private mechanisms satisfies epsilon times something like k delta differential privacy, where this epsilon is epsilon times square root k ln 1 over delta type term that we saw earlier, plus another k times epsilon naught squared. Questions? Good. Okay, so we have done a fair bit of basics of differential privacy. Let's start doing some machine learning. So I'll start with kind of one of the basic problems in unsupervised machine learning, which is called principal components analysis. I guess I chose this because this is kind of, in this case, the mechanism is particularly simple and easy to explain. And actually has all the nice properties that you would want from a differentially private machine learning algorithm. Okay, so what's the PCA problem? I expect most of you have heard of this, but let me just set up the framework. Here we are given a set of n data points, x1 through xn, in some d-dimensional space. Think of d being fairly large. We'll assume that each one of them is normalized to have norm at most 1. And my goal is to find a k-dimensional subspace which captures the most energy of this vector. So I want to maximize, I want to find a projection, a k-dimensional projection matrix by k. This is the norm of the projection of xi to the subspace. And I want to find the subspace such that in this subspace the total energy is as large as possible. If I write A as a matrix where each of these xi's is a column matrix, then a classical fact in linear algebra says that this maximizer is defined by taking the top k eigenvalues of AA transpose. So you look at the covariance matrix of your data, that's AA transpose. You look at the top k eigenvectors, that should be eigenvectors, sorry. And if you look at the span of the subspace, span of those k eigenvectors, that's the subspace you are looking for. Why do we want to do PCA? It's a very useful subroutine for reducing the dimensionality of data. If you believe that your data actually lies in some low dimensional subspace, which is your signal, and there is some added noise which can be in full dimensional, then PCA would be a way to kind of get rid of the noise dimensions. And this is actually a very, it's a surprisingly powerful algorithm, not just in theory but also in practice. So for example, for doing recommendations for the Netflix challenge, this algorithm is actually a surprisingly strong benchmark. If you believe that people's preferences about movies lie in some low dimensional subspace, we can try to find the subspace which find the PCA subspace and just use those projections to predict movie preferences. Okay, so let's do private PCA. So now we want to compute the subspace still, but we want to make sure that individual xi's get their privacy. So we'll think of two data sets as neighboring if they differ in one column or in one of the vectors. So A will be the matrix which has all n data points. A prime will have one of the columns replaced by 0. So I've removed my data from the data set. Okay, so let's look at the covariance matrix. There's kind of two possible covariance matrices, one for A and the other for A prime. The covariance matrix A transpose is essentially just the sum of xi transpose over the n people in the data set. So the difference between the Ci compute on A and the Ci compute on A prime is exactly xi times xi transpose. So let me look at this matrix C minus C prime. This is sort of my global sensitivity. The Frobenius norm of C minus C prime is just the Frobenius norm of xi transpose. And it's not hard to see that this Frobenius norm is just the square of the 2 norm of xi.
Sorry, so the A prime is you removed one vector in all zeros?
Yes.
With another vector.
So you can do that. That's kind of 2 steps. So we would get a factor of 2. For simplicity, I'll just assume so I guess you can define differential privacy with respect to either changing my data or adding or removing my data. Here I'm using the removing my data definition. Okay, so what does this mean? I have said that the Frobenius norm of C and C prime, of C minus C prime is at most 1, which means that if I take this matrix C, flatten it out into a big vector, an n square dimensional vector, this big vector now has L2 sensitivity at most 1. Why? Because Frobenius norm of a matrix is nothing but the L2 norm of the vector version of that matrix. So now we should all know how to solve this problem. C is a function of the data set which has L2 sensitivity as a vector at most 1. So the algorithm that you should propose at this point is to take this vector and then add Gaussian noise to it. For covariance matrices are always symmetric, so we would like to preserve that property, but that just boils down to saying that my vector that I care about is just the top part of the matrix. So instead of a n by n matrix, I just need to output these entries. These are then fully determined. So instead of this being a n squared dimensional problem, this is a n times n plus 1 over 2 dimensional problem. So, and I guess adding Gaussian noise to this part corresponds to just computing the noise matrix E, where which is symmetric, and each entry is Gaussian. So C twiddle is a quantity I can now publish. And now I can take my C twiddle and do whatever I want to do with it. In particular, I can compute the top K subspace of C twiddle and output that. And because C is close to C twiddle, we would expect this subspace to be close to the original, to the actual subspace. And we'll prove that. But first, just to repeat, this part of the algorithm is just running the Gaussian mechanism. And we saw that Gaussian mechanism for appropriately chosen sigma satisfies epsilon delta differential privacy. So we have a differentially private mechanism when I set sigma to be something pretty small, constant, independent of the dimension. Okay, so let's talk about the utility of this algorithm. We would want to say that this private algorithm is actually a good algorithm. How are we measuring goodness? We wanted to maximize this quantity, the total energy captured by the subspace I output. So the natural question to ask is, how much energy is captured by the output of the algorithm? I want to lower bound this quantity relative to the best possible value of this quantity, overall pi k. Okay, so now I'll use kind of the one of the most useful tricks in linear algebra, which is to write the Frobenius norm as a trace of the matrix transpose. Note that AA transpose in the middle is just my covariance matrix, which I will write as C plus E minus E. Why will I do that? That will become clear in the next step. The C plus E is just C twiddle, and this is a quantity that I will actually know how to control, and I'm left with this term which only depends on E. So far everything is equality, nothing interesting going on. Now I'll use an inequality, which is where something interesting happens. Note that pi k twiddle is the best subspace for C twiddle. So it's better than using pi k itself. Right? So I'm using the inequality that this quantity is at least as large as the same quantity with pi k instead of pi k twiddle. And now I'll substitute back that C twiddle is C plus E. I'll factor that out. This first term is now exactly the optimal value that I was trying to match. What's left is two traces which look like the projection of the error matrix E to a k-dimensional subspace. The nice thing about this is that this E is a matrix that I chose, and it does not depend on the number of points in the data set. It doesn't depend on A. It's just a random Gaussian matrix. So now I can bring in kind of one of a very powerful but relatively standard by now tools from random matrix theory, which basically says that a random matrix E essentially has all eigenvalues roughly square root of t. I'm capturing some k of them because I'm projecting down to k dimensions. So it follows that this trace pi k E pi k transpose, and similarly the other direction, is bounded by k times square root of t. So that gives me my utility result that the amount of energy I capture is at least the optimal minus a small additive term, k times square root t. Okay, let me say a few more things. Yeah.
For the bound you just showed on the previous slide, does that require independence between the projection and E, or does that work for sort of?
It works for all. E, because so great question. The first term can actually be even better because these two are independent. The second term, I'm using the fact that even the largest eigenvalue of E is bounded by square root d. You're adversarially picking some k of them. Good. So this was the bound you get if you don't assume anything about the data set. If you assume, as one often does in statistics, that there's a gap between the k largest eigenvalues and the rest, you can actually strengthen this result using results in matrix perturbation theory and get even better bounds. You would be justified in asking, why should I have to pay this k square root d? Turns out that you can show a lower bound. So using sort of this using this very powerful machinery of fingerprinting codes of Van Ullman and Wadan, you can show that a an additive k times square root d is unavoidable.
But these lower bounds can be avoidable using sort of additional assumptions like coherence and stuff like that? So I remember like Mozart and Eric Price has this paper.
So the results there were actually weaker than the ones we have here. I think the matrices you get from the lower bound construction are actually pretty coherent, or whatever, pretty incoherent. So that won't let you get around these lower bounds. If you make some gap assumptions, then you can definitely get around these lower bounds. Yeah. So if you assume some spectral gap, if you assume that the best k-dimensional subspace is actually a lot better than any other subspace, then you can prove better bounds.
Just a small question. These bounds can also, so this isn't the Frobenius norm. You can translate them to like spectral norm bounds?
You can translate them to spectral norm as well, yeah.
Just square root of k.
Square root of t, yes.
I have one more question. Yes. So, in essence, you're applying the noise after you found the optimal subspace.
No, before. We are adding noise to the covariance matrix and then just running your favorite algorithm to the covariance matrix. But if we did the other way around, if we actually computed the actual top k subspace and then added noise to it, we would do way worse.
But I guess here you're outputting only the subspace, not the subspace time the matrix, of course. Like
yeah, so you can't output the matrix. You just want to output the subspace. Yes. So that's actually a very important point. You could also have viewed this problem as I'm computing a function of my data set, which is this projection. I could have tried to compute the sensitivity of this whole function and added noise to it. That would have given me significantly worse results. So here it was important that I kind of found this this intermediate object in the algorithm, which has very low sensitivity and is very useful for computing the optimum value. And that allowed me to get these very strong bounds. The other nice thing about this algorithm is that the runtime of the algorithm is essentially the same as the runtime of the non-private algorithm.
Okay, sorry, just one more clarification to your question. So when you say you publish the noisy covariance, that is the subspace. That's not the original covariance matrix you were talking about.
Yes, so we publish, so the algorithm can do one of two things. I can actually just publish C twiddle, which is the covariance plus noise, and let you do the top k computation. Or if I have more computational resources than you do, I would actually compute pi k twiddle from C twiddle. But from a privacy point of view, I'm essentially happy publishing C twiddle. Good. And because I can actually publish the covariance, you can do other things with this covariance. You may have a different k in mind than the one I have. You can compute your own k-dimensional subspace. You can also use this for computing a linear regression on the data set because you have the covariance, and that's all you need to do linear regression. And empirically, I guess Orr has done a lot of work showing that this works very well. There he is. Good. So I guess this sort of is a nice algorithm because here we were able to do many things. We were able to prove strong utility bounds for the algorithm. So if we want to do differentially private machine learning, we want to be able to say that the privacy does not come at a large cost. And if we can quantify that, that's very appealing. You can try to phrase that as for any machine learning task, there is an inherent statistical error that's present in the task. Ideally, we would want to be lower than that statistical error. In some cases, we will not be able to be lower than that statistical error, and we would want to be, I guess, ideally want to prove lower bounds, showing that what this algorithm is doing is close to the best possible. We would also like our differentially private machine learning algorithms to be as computationally efficient as the non-private ones. And we will not always be able to achieve that. This was a happy coincidence where we were essentially able to match the computational complexity of the non-private algorithm. And I guess some other nice desiderata of private machine learning algorithms would be, the algorithm should be simple, should be easy to understand. Having small constants turns out to be important in practice, as we'll see in the next hour. And I guess it's also useful if your algorithm is easily extendable. Often in machine learning, we have other background knowledge or other reasons to kind of tweak the problem or the algorithm a little bit. If your algorithm can easily adapt to that, that's very useful. Let me spend just 2 minutes on talking about convex optimization. So I guess a large class of machine learning algorithms fall into this framework of optimizing an empirical risk function. So they look like this. You have some data set x1 through xn, and the goal is to find some parameters, I'll call them w, that minimize the average loss over data points of some loss function between the parameters and the w. This is saying how compatible this w is with this example. For example, if I was trying to do classification, w would define a classifier, xi would be a labeled point, and this loss may be small when the point is correctly classified by the classifier, and large otherwise. In traditional machine learning, this loss function is usually convex. So let's start there. And we'll usually restrict this w to come from some convex constraint set. When we do a differentially private version of this problem, we will not compute w star, but we will compute some w, which is an approximation to w star. And the kind of approximation we'll be interested in is how large is the gap between the loss at w star and the loss at what your algorithm outputs. We'll call that the excess risk. This is kind of a common paradigm. As I mentioned, you can phrase your classification problems as a logistic regression. You can also phrase linear regression in this framework, lasso, support vector machine. I guess often you're interested in a slightly different version of this problem, which is sort of the population risk minimization version. And those can be related. For this talk, it will be convenient to just think about the ERM problem. So I'll just state what's known for this problem. This problem has been heavily studied, and we kind of know what's possible. I guess the important result is this one, which says that if you want epsilon delta differential privacy, the excess risk looks like 1 over epsilon times square root d over n. And this is close to optimal. If I didn't care about privacy, the bound here for at least the population version of the problem is like 1 over square root of n. So this is better in that there's a 1 over n dependence, but worse in that there is a dimension dependence. Unfortunately, that's unavoidable in the most general case. There's lots of different algorithms that work for this problem. I've just stated them here. And this is my last slide, so let me just say a few words about these. So as you can see, 3 of these algorithms, I've put the word Gaussian next to them, which is to say that they are similar to the private PCA algorithm in that we found the right step in the algorithm to add Gaussian noise, and that is how I proved privacy. So privacy was achieved by taking a non-private algorithm and adding Gaussian noise at the correctly chosen steps. Two of them use what's known as the exponential mechanism, which I guess I will mention in the next hour briefly. And one of them is actually a strange beast. It has its own privacy analysis. It doesn't fall into your classical frameworks. Yes?
Unfortunately, I mean, I didn't follow very much of the technical stuff. And maybe in your next part, I would love to hear about a specific application where this might be useful for a company. Sort of following up on some of the discussion we had in the previous.
Yes. So we will see an example of a specific algorithm, its analysis, which is actually and actually some real numbers for a specific application. Yeah. Okay. I guess I am out of time, so we can maybe do a few more questions, or
We've got, you know, if people have one or two questions now, that would be great. Now's a good time to ask. And otherwise, if you want to digest over lunch and bring those questions to the next part of the tutorial, then that also works. Okay, so let's stop for lunch. Let's thank Kunal again. Yeah, so we resume at 2 o'clock, and lunch is on your own.